Okay, so, well, thanks for inviting me here, get me again to speak. And at the last GSI conference, I gave an overview of a kind of approach that I'm trying to develop to think about language in a sort of more geometric way. And so in a sense, this is an update on what I talked about back then. And I'm actually going to focus on a few things today that are really work in progress. So, the papers hopefully will be out sometime soon. And I'll say whatever, the current state of the thing is with some of these things. And there's a few other papers that are already out on the archive, some of which I had discussed in my talk back then, and some I'll mention today. And I'll make the slides available, so I don't mind. So in a sense, the general question, if you want, there's been a lot of work in recent years on computational methods in linguistics. And a lot of this work has applied, has focused on very concrete and important questions like, creating efficient machine translation and so on. And a lot of the time, this relies on some statistical analysis of some very large corpus or very large corpus of text and trying to, create a kind of machine that will provide better translation. If you use things like Google Translate, you will notice that it has improved, very significantly in the last few years, and that's an effect of this type of computational analysis. However, the point is that there's another set of questions which are a little more theoretical about how language is actually structured and how it functions. And these kind of questions have been somehow bypassed by the current way of thinking about, computational way of thinking about linguistics, whereas linguists themselves are very interested in understanding these more theoretical questions about language. And so, if you want to summarize some of the questions that are considered important by linguists, one is how language acquisition works. How do we actually get to learn a language? What does it mean to learn a language? How does our brain converge on a certain kind of structure that's proper to one language and not to another one? And how is language, in particular, a kind of syntax calculator that we use wherever we produce language? How is that actually stored in the brain? What is the neuroscience counterpart of that? And also, linguists know that languages evolve and change over time, so what are the rules, what is the dynamics that drives language change? And can one make quantitative and predictive models about that? Of course, these are very broad questions, and it's not, they're more like general programs of what linguists like to study. But the question, how can you try to use some mathematical methods to at least start to explore some of these questions. And so, first of all, when you think about language, you can think of language at many different scales. There's, if you think of the basic unit of sounds that exist in a language, you look at the language at the smallest scale, which is the phonetic one. If you think about how a language modifies words, whether it has conjugation, certain type of conjugation of verbs, certain types of cases or stuff like that, you're looking at words as your basic unit of measure in language, and that's the morphology level of language. If you think that the basic unit is a whole sentence, then you're looking, in a sense, at the large-scale structure of language, which is syntax. So what for my own interest in thinking about language, I want to focus on this large-scale structure of language, so how syntax we describe. And so one idea that has been developed by linguists is this idea, this principle and parameters model How syntax started out being developed by Chomsky in the early 80s, has since been studied a lot by linguists. And it is very appealing from a mathematical perspective because it's the idea is that you want to, in a sense, parameterize the possible syntactic structures of languages in terms of a certain set of binary variables. A binary variable is an answer to a yes-no question, so you can think of it as, is a certain construction possible in a certain language? If yes, your parameter, your binary variable is up. If no, it's down. Okay, this is a nice idea, but there are some problems with that. And one of the problems is that, let me maybe make an example of what I mean by this yes-no type of questions. For example, it's known that certain languages are head initial and certain languages are head final, which means that when you construct the parse tree of how you're supposed to read a sentence, if your sentence is an English sentence, the head of the sentence, which is in this case the verb, is at the beginning of the sentence. If your sentence is Japanese, it's at the end of the rest is appended in the opposite direction. So this is a case where there's one binary variable which is set one way for English and is set the other way for Japanese. And there's several languages where the head is set one way and the head is set it another way. There's certain other examples like that. So here's an example that's very familiar to the French speakers, right? If you, in the Romance languages, in French, well, you can say il pleut, you cannot say pleut without dropping the subject, but in Spanish and Italian, llueve or piove is a perfectly grammatical sentence, and the verb is essentially the same in all these three languages. These languages are extremely similar to one another, but there's one thing you can do in Italian and French, and you cannot in Italian and Spanish, and you cannot do in French, and it depends on this binary variable being set one way or the other. So this is the idea. There's a lot of examples like that, and however, there are some basic problems with this very nice idea. And one of the problems is that there are many of these binary variables linguists have studied, classified for a lot of languages, but nobody has even a conjectural description of what the complete list of these variables should be. By complete list, I mean a list that if you are able to determine the values of all of those variables, then the syntactic structure of your language would be completely determined by just knowing those values. And this is obviously a little missing problem. But another even more important probably issue is the fact that even for those variables that are known and classified, it's not known what relations there are. So what is an actual set of independent variables, and what are the dependencies between all of these variables? It's known that there are dependencies, so there are examples where it's known that if a certain parameter is set in a certain way, this forces another parameter to be set in another way. But there's not, I mean, certainly we are convinced that they don't know the set of relations between these parameters. And okay, so there's other points. So these syntactic parameters are dynamical variables. Historical linguists, in languages for which written text go back several thousands of years, like some of the Indo-European languages, it's possible to trace changes in these syntactic parameters that happened by effect of interaction with other languages. And so that's, another thing that one would like to understand, what is the dynamics that leads to this type of changes. And another issue, the problem is that collecting data is hard. So of course there are languages that are very well known and for which there's a lot of text and so on. But I mean, collecting data, the syntactic structure of languages is more difficult than thus collecting lexicon of a language. So especially for languages for which they are not spoken by very large populations, some linguist actually has to do the field work of going and recording enough information about the language to pin down. So there are some databases, And what we've been working mostly with is this one that's called Syntactic Structures of World Languages. It's an open database that's available online, and a fairly large data set. So these are kind of independent data sets in the sense that they collect different type of syntactic parameters, which is good. So you have like different sets collected in different ways that one can use to compare the type of information that you get. And there's some, so this another database that's supposed to supersede this one and incorporate it, but it's still being built. This is a database that's mostly about morphology. It has a bit of information about syntax, but not very much, so it's not terribly useful for this point of view. And so the SSWL one collects a few hundred languages and about 100 parameters, a little more than 100 parameters. But I mean, there's some problem with this, because as you can imagine, if you pick a set of a few hundred languages, some of these languages will be mapped extremely well, and some of these languages will be mapped not so well, because not all languages are equally accessible, equally documented, and so on. So one has to deal with these discrepancies in the data set and so on. The more recent data are better because they are more uniformly mapped, but they only include mostly Indo-European languages. So there's a set of, one has to deal with whatever data are available. Obviously this data will increase over time, but it's that's the limits of what one can do at this moment. So what kind of questions wants to look at? So one type of thing that linguists study is in a sense, the genealogical trees of languages. So we know the languages come in family, and there's been a lot of work, especially the Indo-European language family is being studied by linguists for now some centuries, and mostly by actual philological analysis of texts, and trying to trace back the history of the languages and how the branching of this tree happened. But of course, you cannot apply the same technique to languages for which there are no texts dating back, which one can observe in the development from the ancient languages to the modern ones. One can at best collect information about the modern languages, and one would like to still be able to reconstruct a reliable genealogy tree of the modern, starting only from data about the modern languages. So the question is, how can one do that computationally using only information about the modern languages? So there are, even about the Indo-European tree, which is the best studied phylogenetic tree of languages, there are still controversies when you go deep towards the root of the tree. I'll mention that in a moment. And so a lot of, yeah.
What is phylogenetic algebraic geometry?
I'll come to that in a moment. So there's so a lot of these attempts to reconstruct these phylogenetic trees have been used using lexical data. So you have standard lists of words that exist in a language, and you try to identify cognate words, and you decide the level of proximity between two languages by the amount of cognate words. This has obvious problems. There are synonyms, there are loan words, there are false positives, and all kinds of problems like that. In a sense, syntax is a lot more, in a sense, robust and information about the language than the lexicon. The lexicon is very transient between one language and another, but the syntactic structure is more robust. So the proposal is to actually use syntactic structures as a way to do this computational reconstruction. So there have been some earlier results by linguists, Longobardo and Quartiano, using some data set of syntactic parameters. And the idea is to just try, the idea they use is just to try to construct phylogenetic trees by comparing the Hamming distances between these syntactic parameters viewed as binary strings, and then using a neighborhood joining method to reconstruct the tree. One problem with this is that this type of computational method has the problem that as you go deeper into the trees, errors amplify nonlinearly. So at some point you can lose control over how good your reconstruction can be. And so in particular, if you combine that, so we know that there are probable errors in the data set, or some languages are not as well mapped as others, and you don't want these to, you want to have some way of controlling how much the errors amplify as you try to reconstruct the tree. So there's a bunch of computational tools that actually have been developed by people doing this type of phylogenetic tree reconstructions in biology, but the problem is essentially similar, so you can apply them to this setting. And so if you just plug in the entire database of languages and parameters, you find that there's a lot of problems in the reconstruction. So yeah, this is very far from being a tree, obviously, and that's just the fact that it says that there's a lot of ambiguity in the choice of a possible candidate tree. Okay. And if you analyze better what is happening in various regions of this type of computational reconstruction, just plugging in one of these packages that do phylogenetics for biology. And you find a lot of very specific kind of problems that happen. So you find misplacement of languages within the correct language families, but comparing two cases where linguists actually know like certain branches of the Indo-European tree that are very well understood. So where you know what the correct tree should be, you find places where the language is placed in the right tree but is misplaced in the position in the tree. You find placement of language in the wrong subfamily tree. And you find proximity of languages from unrelated families. So it could be that some languages from different families might accidentally have certain kind of syntactic structures that look similar. So you have to take that into account in how you do these reconstruction trees. And so it also incorrectly places some of the ancient languages for which the parameters are known, and so on. So one way to try to do better is to use a different approach, which is actually also being developed for purposes of application to biology, but it actually works in an even nicer way in linguistics for the reason that you have binary variables instead of 4 bases DNA. That simplifies some of the geometry. And so if one tries to do that, so what is the idea of that? So you think that the tree that you're looking for, so that your evolution in this tree has started out as some root with a certain distribution of how the various variables, so the variables are the syntactic parameters, were distributed, they're at the root of the tree. And then it sort of evolved as a Markov process on this tree where these binary variables are independent, identically distributed variables. There's an obvious problem with this assumption. We know that they are not independent variables. So but okay, in first approximation, let's pretend that they are and see what happens. And so you have this kind of Markov model on the edges of the tree. And so this means that the probability distribution of how the parameters are expressed at the leaves of the tree is some kind of polynomial function of these hidden Markov transition probabilities and the distribution at the root. So there's a kind of sum over histories of how you go from the root to the branches of the tree. And the fact that this is a polynomial function of these variables means, in particular, that you can deal with it using geometric techniques from algebraic geometry. And so you have a polynomial map from the number of variables from two affine spaces in these variables. And this is the distribution that you observe at the leaves of the tree. And these are the hidden parameters on the tree. And this defines a certain algebraic variety. And there's a result, which had actually been developed for the biology applications, that says that actually gives you the explicit generators of the ideal that determines this variety. And they are actually 3x3 minors of certain matrices that are obtaining by flattening these tensors. So what it means by that is that if you have a tree and you remove an edge, that separates out the leaves into two sets. So you can write your distribution of the leaves as a matrix in that rank. And so you do that for each edge of the tree. You get a bunch of matrices. You compute all these 3x3 minors. It's a mess, but you do that, and that gives you all the generator of this ideal. So the point is that this is going to be a different thing for each tree, for each possible tree. And so if you're looking at the correct tree, then the boundary distribution that you observe is a point on this variety, so all these functions should vanish at that point. If it's not the correct tree, then you're off that variety. And so you test that by computing, so you take your data for a certain set of languages that gives you certain frequencies of occurrences of the parameters in this set of languages, and you produce a candidate tree with one of these software packages that produce a bunch of candidate trees. And you test, compute all these minors of the corresponding matrices, and you evaluate them at this distribution. So, of course, because you expect that there are some kind of errors in the way the data are recorded. In general, you don't expect that you will get exactly a zero of all these polynomials. But if you are comparing different trees, you can assume that the better candidate is the one that gets, for which this is closest to being a point of the, so it's closest to being on the variety spot. It might be off, but if it's not that much off for one choice of a tree, it's very much off for another one, then you expect that tree is the better candidate. Okay, so that's the idea. So if you test this out, yes.
From the general strategy, what is the advantage that one has compared to minimizing, for example, KL divergence from the variety?
Well,
like the maximum likelihood approach.
Yeah, so I mean, this just seems to eliminate some of the errors that you see appearing when you apply other methods. So, for example, you apply it to some small sets of languages where you detect that there was an error by using some of this, and this eliminates it.
No, but the tree methods that you proposed before, where you don't have a tree, actually, I guess that's the method of Andreas Dress, who developed this phylogenetic tree reconstructions. I'm referring to something different. Mm-hmm. I'm referring to the information geometric approach, where you basically measure the distance. We don't have any distance here. We have some description of the variety in terms of a polynomial. Yes. And the most natural way to actually analyze if this is could come is an element of that variety is to measure the distance from that variety in terms of KL divergence.
That's right.
So I understand that this is a different approach, but I would like to know the advantage.
No, I agree.
This,
so the one you're saying is a little more refined because you actually use a better distance for them saying exactly how far your point is from the variety. Here is just you evaluate the polynomials and you see how large is the value at that point compared to being zero. So it's a little more less precise a method than doing it with distance. What I'm saying is that already by doing it just in this simplified way, you see that it corrects some of the problems. So presumably if you get like a still better solution by actually using a better distance, like you're saying, to measure the position of the point with respect to the variety. But you're right, that's like a further refinement of this. So what I'm saying here is just that, if you take some simple examples of, small enough subtrees where, just by applying some of these compilation technique, it places some languages in the wrong place, so it picks a wrong candidate. You see that, this method picks the correct tree. So, for example, by applying it to this set of syntactic data, syntactic parameters, was misplacing the position of Portuguese in the tree of the Romance languages, whereas if you compute it using this method, you get the correct shape of the tree.
How do you know which one is correct?
Well, this is a case for which the linguists know everything, because so I mean, I'm just testing it on cases where there's no doubt what the correct tree should be, just to make sure that it's working. So, but I'll say that some cases where this isn't yet a good. So So this is some examples where it says that actually on cases where you can test things, like for example, another case where you had misplacements just by applying the lib to the set of the Germanic parameter of the Germanic languages. Using this method, you get the correct tree, as this linguists agree that it should be. And so at least you can see this. So the one problem, of course, this gets computationally easy when the tree grows in size. So a way to do that is to actually build these trees by smaller. So this also avoids the problem that you can have accidental syntactic similarities between languages that belong to different families. So you build first smaller trees, and then you build larger trees from those, and so on. But okay, let me come to a point where actually there are some problems still that we want to understand. So one of the questions is what happens when you go into towards the root of the tree of the Indo-European languages. So that is still something where there are controversies among linguists, because some of the early languages are not as well understood, or not enough. There's not enough data about them as the modern language or the less ancient languages. So, for example, there are certain questions about the relative positions of the Hellenic branch and the Armenian subtree, the position of Albanian in the tree, the split between the Anatolian and the Tocharian branch of these are all things that happened very early on in the history of the Indo-European languages. And in particular, there was a controversial claim not so long ago by a kind of a computational reconstruction of this tree done on the basis of lexical data, and which seems to differ significantly from. So Gray and Atkinson are biologists, and they use the computational methods used in biology, but based on lexical data. And linguists have done an analysis of morphological data, which is more reliable and gives a very different answer. So there was a whole controversy. There's a very nice book that discusses this whole story. And so these are the two trees look rather different, but I want to focus on a small portion of this tree where a difference occurs and try to see what happens there. So here's the portion where these two trees differ. So this is the branching between the Anatolian and the Tocharian part, and the respective positions between these other languages, Albanian and Greek, Tocharian and Armenian. And so the question is what syntactic parameters can say about this. Obviously, this is because these languages are mapped rather poorly in this data set of syntactic parameters. So, one shouldn't trust too much what happens out of it. But so if you use this phylogenetic algebraic geometry method on these SSWL data, this seems to favor the tree that the controversial one, the one of Gray and Atkinson's. Unfortunately, there's this other data set which is more reliable, but it doesn't include some of these languages, so that doesn't. So this is just a cautionary remark that although this method looks quite promising. It might, the incompleteness of the data set, especially when one goes to these very early languages and other issues like that might, make it, yes.
Silly question of a layman. Is it fair to say, looking at the picture, that Albanian is closer to Greek than to Armenian, or is it not fair to say?
That's right. That's one of the questions. Is Albanian closer to Greek than Armenian? And so, according to these three, it is, and according to this, the other one is not. Yeah. So that's there are questions like that. There are not. On which there is no agreement. So certain parts of linguists are in general agreement of what the correct tree should be. It is an example where that's not the case. Linguists are debating what the situation is. Okay, so let me, this is one aspect, this reconstruction of phylogenetic trees. But let me just illustrate some other things that one can think about, in terms of these syntactic data. So one thing that we're really trying to understand is how these syntactic data are spread out in a group of languages. That's partly what these phylogenetic things are analyzing. If you look at these syntactic features and you're given a certain set of languages, how are they distributed among these languages? Are these languages very similar at the syntactic level? Are they not? Which ones are closer than others? So there's a different way you can think of it. You're handed a set of languages. Each one of them has an associated binary string. So you have a set of binary strings, and you can think of that as a code, a binary code. And so you can look at it as a binary code and think about what the position of this code in the space of codes will tell you about the way that the syntactic features are distributed within this language family. So if you just momentarily forget that we're talking about languages and syntax, so if you have a code, so you have you have binary strings of a certain length, n, for n, large n binary strings of a certain length, n. You can think of them as being a certain subset of f2 to the n. In general, these will be unstructured codes. There will not be linear codes. And, but you can compute the code parameters. I think this is, you're looking at how good the encoding and decoding is by this code. So the rate of the code and the minimum distance of the code, the relative minimum distance. So this is now the hamming distance, minimum hamming distance between code words, normalized by the length of the code. And this is the logarithmic cardinality of the code, normalized by n. So you can see where this point lies in the space of possible code parameters. And in a sense, that gives you some kind of information about something that measures like the syntactic complexity of this set of languages that you're choosing. What I mean by that is that if these words are all very similar to one another, so these syntactic features are not very spread out in this set of languages, your code is going to be a rather poor code from the code theoretic perspective. So it's going to lie way down in the space of code parameters. And whereas if it's high in the set in the space of code parameters, this means that these syntactic features are distributed in a much more interesting way within this language. So there's like more syntactic complexity within this language. That's what I mean by that. So these are the code parameters, transmission rate and relative minimum distance. And so they tell you how efficient are the encoding and decoding. And so in general, error correcting codes, you want to optimize both of this. So good codes are the ones for which these parameters are as high as they can be. Of course, you will know that if you try to make one of them high, the other one typically gets low. So there's some constraints about how good you can make a code. And there are certain bounds on code parameters. Well, the Gilbert Varshanov curve is depends on this Shannon entropy. So this is more generally for QRE codes. We're looking at binary codes here. So this would actually be the actual Shannon entropy for the binary case. And so this curve in the space of code parameters is the curve that represents the typical behavior of random codes. So if you have codes that are in the Shannon random code ensemble, they typically collect around this Gilbert Varshanov bound. So if you, in a sense, it's another way of saying, are these syntactic features distributed among languages really as a kind of a uniform random process or not? So if they were, then you would expect that when you look at these codes made by choosing sets of languages, they would all lie around or below the Gilbert Varshanov bound. If you find things that will lie way higher than the Gilbert Varshanov bound, then it would be a clear sign that the way that syntactic features spread across language families is far from being just a uniform random process. And again, you expect that to be the case because there are all these relations between these parameters that affect the way that they dynamically behave. And so you would expect that they will not be all in that random code ensemble region. So in fact, this is exactly what happens. So, well, there's actually other bounds that exist, other interesting bounds that exist in the space of code parameters. Well, a simple bound is the Plotkin curve, is just an upper bound for the very upper bound for the Gilbert Varshanov bound. There's an intermediate bound, which is the asymptotic bound, for which you can prove the existence, but you don't have an explicit form for the function. And it's more, so in a sense, the Gilbert Varshanov curve is related to entropy, to the Shannon entropy, and in some sense, it's the typical behavior of random codes. And it can be shown that, there's actually some earlier work that I did with money, and it can be shown that this asymptotic bound is related to the Kolmogorov complexity of codes. And it's, so codes that are above this asymptotic bound are really the kind of most interesting codes from the code theoretic perspective. The examples that one knows are usually coming from algebra geometric codes, so they're very kind of very structured objects that behave differently from your typical codes. So, but it's generally difficult to construct codes above this asymptotic bound. And so here's what happens when you look at you explore the syntactic parameter database, and you pick, for example, all pairs of 2 languages or 3 languages, and you look at all these codes, and you plot their position in the space of code parameters. So you find that a lot of these choices of random choices of 2 or 3 languages actually do populate the lower region. And they populated in this interesting shape. Well, this is not, it looks strange at first, but it's not so strange because it really is this Tomaev function. And for the reason that you're sort of fixing the cardinality of these codes and looking at their distribution, so they tend to distribute like this. So this kind of really behave like random codes. But there's actually a lot of outliers. So when you start to look at larger sets, languages, and you plot where it goes, so here down here you see a superposition of several of these Tomaev functions because you look at different cardinalities of sets languages. But you find a lot of outliers that actually, so this is the Gilbert Varshanov curves. These are the ones that kind of behave like random codes. And these are already interesting because the asymptotic bound, so this is the Plotkin bound, the asymptotic bound is somewhere in between here. And these are outliers even for the Plotkin bound. So there are codes that actually go very high up. So they're very far from being this type of a uniform random process behavior. Okay, so
what it means that there exist outliers?
What it means? No, so it means that whatever dynamical process has produced the distribution of syntactic feature across languages that one can observe, is not this kind of identically distributed uniform variable. And you can, so this kind of confirms that it's, otherwise they would all be in this random code region. And so there's something that's deviating significantly from that hypothesis. And we sort of know that the reason is that the fact that these variables are really not independent variables, and their relations is constraining the possible dynamics that goes. So this is just a way of observing the deviation from that type of variable, quantifying it in terms of some measurable parameters. So this means that, if you want to try to construct dynamical models for language change, you kind of have to take into account this type of interaction between the variables. So this is an earlier paper where we just took the simple idea that you have these binary variables. And what linguists know is that through the evolution of languages, some of these syntactic features have changed by effect of interactions between different languages. And so, I mean, as a physicist, you want if you think of something like this, the obvious model that comes to mind is something like an Ising model, a spin glass model, where you have spin variables that tend to align by interaction at vertices of a graph that tend to align by interactions along the edges. However, if these were all independent variables, then you would simply have uncoupled Ising models for each of the syntactic parameters, and it would just, the equilibrium position would just reflect the prevalent distribution in the initial conditions that we'll have. But that's not what happens because, for example, we looked at some of the data, linguistic data, where one knows that one knows some of the relations between these parameters, and actually trying to input those relations in the Hamiltonian of the system. So you think of languages at the vertices of a graph and interaction along the edges. And there's some interesting information about what the temperature means. It's in a sense measure the amount of interaction that is happening. And it can be more detail, but. So let me just say that the way so the kind of relations that are known are generally relations of this kind. You have two parameters where if in a language the first parameter, say, has value up, then the second parameter can be anything, either up or down. If the first parameter has value down, then the second parameter is actually undefined. It just kills the second parameter, so to speak. So you can input a relation like that as a kind of Lagrange multiplier in your Hamiltonian by creating a term that favors energetically this type of configurations. And if you do that, then you see that you get to equilibrium configurations that are not just all the spins align with the prevalent distribution, and you get some more interesting equilibrium configurations. But I mean, there's a problem with that, which is that if so this works, you do the usual kind of metropolis algorithm and so on. This works if you try it on a very small, like a small set of languages and small set of parameters. Then you do see this kind of interesting, the equilibrium configurations. But when you try it on a realistic model, like a dataset like this with 28 languages and 63 parameters, computationally you don't it becomes computationally hard, so you don't no longer. You lose control about the convergence process of this dynamical system. However, that's again where this coding theory perspective becomes useful, because you can actually look at the induced dynamics on the space of code parameters if you think of the corresponding codes and as you run these dynamics. And in some cases, you do see the convergence starting when you look at the induced dynamics on the space of code parameters that you don't yet see by running this full dynamical system on the thing. So it's also suggests that it could be maybe a useful method to explore this type of dynamical models. So that's one other aspect of the story. Well, let me come to trying to understand better what the relations between these parameters are. As I said, some relations are known by linguists, but linguists expect that there is a lot more relations that we don't know. So of course, if you want to start to explore what kind of relations you can have, you want to try to dimensionally reduce your set of data and to make it more manageable. So here, if you try to just simply try things like principal component analysis, it's difficult to extract some useful information. So we actually tried something different. There was an approach that there's were a few papers I mentioned, one of them a few years ago by Belkin and Yogi, where they considered a kind of heat kernel way of dimensionally reduce a set of data. So and which turns out, they give several explicit examples, turn out to sometimes work better, more efficiently than things like principal component analysis. So the idea is, well, so you have a certain data set, which in general lie on, you think of them as being lying on some manifold inside some large Euclidean space. You don't explicitly know the manifold, you know the data set. And you want to project it in a meaningful way on a lower dimensional space. Yes, on a lower dimensional space, so that you keep as much information as possible on the proximity relations, but on the what you expect to be the relations between these data points. So what you do is you construct some kind of adjacency graph. You can do it in different ways: epsilon neighborhood, nearest neighborhoods. And then you attach weights to the edges, and they propose to do it in this kind of discretized heat kernel way. And so this introduces two parameters. One, you have a size of the epsilon neighborhood size that you look at, and you have a heat kernel parameter t. So within this space of parameters, you can look for best representations. And what you do is you do an eigenvalue problem for the Laplacian of this graph, and you map by the Laplace eigenfunction. So you project on the eigenspaces. And so they kind of prove a certain optimality result of the embeddings that they obtain in this way. So if you apply it to this set of syntactic parameters, it's interesting that, so we have two sets of parameters. One is these SSWL parameters, which is this blue line, and one is this recent Longobardi collection of parameters. And depending on what kind of connectivity you use, with respect to epsilon neighborhood, they behave quite differently. But with respect to nearest neighborhood connectivity, they behave very similarly. And when you start to do this kind of look at this kind of graphs, so you see that according to this epsilon neighborhood, you start to see certain clusters of parameters that go together, and you get certain informations about parameters that are naturally grouped together by these techniques. So there are certain connectivity structures that you see, and in the way this changed with epsilon, so the way the topology of these changes with epsilon, also telling you some information about connectivity, or structure within this data. So in the SSWL, as I said, the epsilon connectivity doesn't work so well. You see smaller clusters, and they don't change much. But with the nearest neighborhood set, you see more structure. So you see that there are certain parameters that have much higher centrality in these networks than other, in terms of you see better the neighborhoods and so on. And this is an example for the other data sets. So you see components and certain nodes that play a particular role with respect to centrality. So I don't have time to try to give you a linguistic interpretation of what this means, which is still under construction, but that's what the data analysis suggests. That there are interesting structures in the way these parameters relate to one another. And when you explore this epsilon t space region, the connectivity and the epsilon neighborhood and the heat kernel parameter, you can look at places of maximal variance, where you see maximal variance, would be the parts that most interesting to look at. And so this is like a plot of variance contours according to these two parameters. And what comes out actually is there's a preferred size in the epsilon variable. There's like a Gaussian. There's a preferred size where you seem to see maximal variance, and that's I still don't have a good interpretation for what that means. So it's still work in progress. But there seems to be a specific scale that's relevant, especially relevant. So there's a bunch of further questions, especially you like to actually try to reconstruct the manifold on which this data point, what you can say about the manifold on which these data points live. And so I think I want to probably stop here. There's some interesting that I did talk about in my previous talk about a persistent topology of this data set. And I just maybe want to say that so if you do the topological analysis of this data set, you find some kind of interesting structures. So you find some persistent first homology. So topology depends on language families, and you find some persistent first homology in the Indo-European language. And so we did this analysis for the SSWL data earlier. And we just say that if you do it again from the new data, you still see the same kind of structure. So it seems to be something that's not dependent on which type of syntactic features are collected, but actually of the relation between these languages. And we had some possible linguistic interpretation of what this means. And there's a lot of more smaller scales structures in persistent homology that definitely call for some more, more in-depth analysis that we haven't done yet at this point. DH0, the connected components of the persistent homology, so it should in some sense mirror what the phylogenetic trees are seeing. So, and they seem to do that, but that's still not completely understood. So, so this is kind of a longer project. So this is just an update on some of the aspects of this project. The longer term, again, back to the main questions that linguists are interested in, and what we would like to try to address with this. And that's obviously a much more long-term goal. But okay, I'll stop now.
We have a few time for little questions. For questions.
Yeah, thank you. For these parameters, okay, what is the importance of exception? That is, do you have, for example, language where mostly a rule is followed, an exclusion, or but sometimes it's possible to.
So
so you don't have only 0, 1, but you could have something like a probability.
Yeah, so that's right. So one thing is that when you also take into account these relations between the parameters. So, like for example, the ones that I mentioned, that a value of one parameter can make another one undefined. You might have to allow something a little more than binary variables, because you want to have like a 0, 1 and an undefined value for certain parameters, so it's more like ternary variables. Yeah, so a lot of these settings like first approximation things. Again, these connective, so yeah, maybe we can discuss it more.
So another question is about the graphs, okay? Because after that, in your talk, so the phylogenetic graphs, okay? After that, you admit that it's not like species, okay? Because in the language interacts, okay? That people continue to exchange, okay? And in some sense, that language continue to evolve together, okay? So they influence themselves. Mm-hmm. So do you have looked at some structure which is less constrained than a graph? For example, a string permits to do that. I take a closed string, it permits to say that I have a language which is still more connected or less before or less after, depending on the parameters, for example.
That's right, yeah. Yes. So, yeah, I mean, some of these things to explore exactly how these things behave, but yeah.
I have just one comment. Maybe there is maybe another way how to use geometry in the reconstruction of these phylogenetic trees, and it's a work by Ruriko Yoshida from Kentucky University. And she uses the polyhedral geometry, and the idea is that every tree is encoded by a certain vector in highly dimensional space, and it's evaluated, expected distance in some measure, like Hamming distance of factors, and collection of all these vectors, you can a convex hull, and it's some polytope, and you try to find facets. And then, if you have given some distance, so you can try to estimate the best by methods of linear programming.
Yes.
So I wonder whether you know, or whether.
Yeah. No, I mean, you're right. I mean, that might be, yeah, that might be a good thing to try with this data. I mean, as I said, I just illustrated like the most naive thing you can do in that direction, which gives you some result. But yeah, there's more refined constructions like.
Okay, let's continue discussion at the coffee break, please. Thank you, speaker.